So my name is Tracy Dean. I'm an offering manager in IBM. I'm responsible for some ZVM tools. I'm responsible for some IMS tools, but I also have some sessions that I teach at IBM conferences and customer conferences around Rexx. So I'm sharing part 2 with you today. So let's get started. So in part 2, remember in part 1, what we did was we talked about what the Rexx products were. We talked about external environments. We talked about instructions, functions, and subroutines and variable visibility in those. And then we talked about parsing. So in part 2, we're going to pick up where we left off, and we're going to talk about compound variables versus the data stack. We'll talk just a little bit about I/O. We'll talk about troubleshooting, and then, of course, programming style and techniques, which is always a very personal decision, but I'll make some suggestions if you're looking for them. And then I'll wrap up talking about other Rexx products and projects that are out there related to Rexx, but not specifically Rexx on ZVM. Some of the material is going to talk about ZOS specific things. I will cover that. I know some of you may also support ZOS. So there are some things in Rexx that are specific to ZOS when it comes to the data stack. So I will cover those slides, even though I know the majority of your interest is ZVM here. Okay, so let's jump in and talk about compound variables and the data stack. So what is a compound variable? So a compound variable or a stem, I think of them in other languages as arrays. So it's a way to have multiple things, multiple entries stored with one variable. So in Rexx, we call that a stem variable or a stem array. The variable name is actually the stem followed by some number of tails, okay? The stem actually is just a simple variable that ends in a period, and then the tail is the number or more variables on the end. You can have multi-dimensional arrays, if you will, because you can have multiple tails. So it's not just simple arrays, you can have multi-dimensional arrays as well. So remember when we talked about variables in the previous session, remember every variable, if you have never given it a value, Rexx defaults it to the name of the variable in uppercase. So that applies to both stems and tails in arrays as well. And so when you have the variable day.1, if you've never assigned a value to that particular stem and tail, then the default values are the stem of day in uppercase followed by the dot, and the tail is the number 1. Similarly, if you have array.j, so I haven't specified an actual value for the tail, I've specified another variable, resolved to array in uppercase for the stem with a dot at the end, and then the tail would be uppercase j. So that's only if you've never assigned a value to that particular entry. If I did something like saying name is equal to Smith in quotation marks, so a literal value, and phone is equal to 12345, then if I did employee.name.phone, the value would be employee in uppercase with a dot at the end, and the tail would be Smith.12345. So that's a general idea of working with stems and tails and how the values are going to be initialized. So what if I actually wanted to initialize a whole stem variable? I didn't want to have to loop through and initialize every value. I just want to initialize the whole variable so that every stem and tail combination results in an initial value. So let's look at an example here. I could easily say month dot in the middle here is equal to, and I could put empty quotation marks there. So I'm initializing it to null. So then if I said say month.6, the value would be a null. So month.anything is going to be a null unless I assign it something else. If I do a set of commands up here, I say month.12, then the value is going to be month.12 because I've never assigned it anything. I then say month dot is equal to unknown. I say month.3 is equal to March, month.6 is equal to June, and now the value of month.12 is unknown, but the value of month.3 or month num is equal to March. Okay, so very simple ways to work with stem variables. Some people also, if you're using very large stem variables especially, you would want to get rid of the variable. So once you've referenced a variable in memory, Rexx is keeping track of it, waiting for you to change the value. So if you're using a very large array, that might be a lot of variables in memory. And if you want to signal to Rexx that I'm done with this stem variable, I no longer need it anymore, you can remove all references to it, then I can use the drop instruction. So drop month dot reinitializes everything back to its initial value as if you never gave it a value to start with. Okay, people did that in the old days, if you will, when they had memory constrained environments. That's not typically a concern these days unless you're using very, very large stem, but also by doing this, it avoids no value errors. So typically we want to drop it so then we can kind of reinitialize it again. So how would I process compound variables? Many people might already know that the .0 value, when you use the 0 as the tail, that's the number of things in the array. So the number of tail values that there are. That in Rexx is actually just a good practice. It is not a requirement. You will not get any kind of syntax error in Rexx because you did not use that convention. But it is a convention and it is good practice. So what often see is something like the do loop that I have here. I have invitee.0 equals 10. That means there's 10 things I want to process. I say do j equals 1 to invitee.0, so 1 to 10. I put a message on the console saying enter the name for invitee and then the number that I'm on, so invitee 1, 2, 3, all the way up to 10. And each time I do that, I pull a response from the console. That's what parse pull does, pulls a response from the console and puts it into the variable invitee.j. So at the end of this do loop, I will have 10 values in invitee.0 through 10, and their values will be whatever names I typed on the console for each prompt. So that's a typical loop kind of thing that you would see, any kind of a do loop that the end of the loop is the invitee.0 or the stem.0. But again, that's a convention, it's a guideline, it's a good practice, but it's not required in Rexx. Many I/O functions, though, will use that convention. So stream I/O, exec I/O, pipelines, they all use that convention. So if you want to write a stem out to a file, for example, the 0 tail needs to contain the number of entries that you want written. If you read a file in, Rexx will initialize the .0 tail to the number of records that it read. So those are conventions that our I/O processes follow as well. Okay, so just awareness around the compound variables. Now you can get a little more complex in compound variables. Remember I talked about having multi-dimensional arrays, for example. And in this case, I might want to use one of the values of the stem as an index into the other values. So let me show you what I mean. I have a file. It has with a column header. The scale at the top here is just for your reference, so that's not part of the file. But the header, employee number, name, and location is part of the file. And then the file contains 3 names with employee numbers and locations. So what I could do is I could use pipelines to read that file. It happens to be named employee info, and put the results into a stem called rec. And then I would say do j equals 2. I want to start at record 2 because I'm going to ignore the header. I'm not processing the header line, so I'm just going to start at record 2. And I'm going to go through until I get to rec.0, which is the number of entries in the file, which is 4. I'm going to parse that variable rec.j, so rec.2 on the first iteration. And I'm going to say I'm going to start in column 1, and I'm going to put the data into a variable called employee number. And then I'm going to remember, if you remember our parsing, I'm going to do blank delimited parsing. So as soon as I hit a blank after employee number, I'm going to stop. And then I'm going to get to the next non-blank character and put it into name.employeenum. So now name.A1234 is equal to M. Kalashaw. And I do that, I put into name.employeenum data starting with the first non-blank character after the employee number, so the M or the T or the V, and I do that all the way until I get to column 25. So remember from our parsing discussions, I didn't want to blank delimit parsing because there may be blanks in the name, right? So I'm using column delimited parsing in order to pick up all the blanks in the name. And then once I get to column 25, I start putting the information into location.employee number. So location.A1234 is going to equal United Kingdom. Okay, so now I've used my first column in the file as my tail for other stem variables. So if I continued on, I read this file in, and then I asked the user, which employee number do you want to learn about? I parse the employee number, I pull in the employee number from the console, I uppercase it so that I can match what's in the file, and then I say the name of the employee, A1234, is, and then I'm stripping the name, right? Remember, because I don't want these blanks that are on the end. So the blanks between W and United Kingdom, between N and Portland, and between N and Austin, it strips those away because I'm using the strip function in Rexx. And then I just insert. And then the same thing with location. I say the location of employee, employee number is, and I strip the location.employee number. So again, I'm reading the file, and I'm using one of the columns as an index into other arrays for data about the file. So that's one way to use compound variables. So compound variables, again, are a way for you to have lots of information. You might not know the size of it right away, and you're trying to process that information all through one variable or one array. So now we're going to contrast that with the stack. So now let's talk about the data stack. So you can have two different types of stacks in Rexx. You can have the last in, first out stack, which means I'm putting things on the top and I'm taking things off the top. So the last thing I put on the stack is on the top. The first thing I take out is on the top. The FIFO stack, or first in, first out, is where you put things in at the bottom of the stack and you take things off the top of the stack. So some people would call this a queue. If you think of like when you're lining up to do something, the last person in line, the first person in line gets processed, and if you join the line, you join at the end. So in Rexx, you must always, always, always remove things from the top of the stack. There is no way to take things from the bottom of the stack. So you have to control the order of processing based on the order you put things on the stack. So if you want a LIFO stack, you put things on the top. If you want a FIFO stack, you put things on the bottom. But you always, always, always take things off the top of the stack. So how do we process stacks? What are some of the commands and functions in Rexx to help a stack? So there's really three basic Rexx instructions, if you will, for processing stack data. And one is the push instruction. And what that does is push something onto the top of the stack. So in this example, I say element 1 is equal to new top element, and I push element 1. Now that's on the stack. The queue instruction will put the element on the bottom of the stack. So it creates that FIFO stack. I say element 2 is equal to the new bottom element, and I do a queue element 2. So now in my stack, the top thing is new top element, the bottom thing is new bottom element. And then what I typically do to pull things off of the stack is I do a parse pull. And remember, it always removes things from the top of the stack. So if I said parse pull next thing based on the previous instructions with the push and the queue, the next thing is going to be equal to new top element because it's pulling something off of the top. Now this is the parse pull command we used earlier to pull things from the console. So the way Rexx works and the way the stack works in ZVM is when I do a pull, if there's something on the stack, I will take that first. If the stack is empty, then I will prompt on the console and wait for user input. So the pull is used for two different things. And if you want to use it for the console, then the stack needs to be emptied, or you can do a different type of Rexx instruction to definitely pull from the console. So how do I know how many things are on the stack? Well, Rexx provides a queued function. You'll notice the name of the function is queued, and there's no parameters passed, but it must have the parentheses there. And that will return the number of things that are in the stack. So in this case, I say number of elements is equal to queued, and now I know how many things are in the stack that I want to process. So just like the .0 tail contains, the queued function will tell you the number of elements, and you can capture that and save it and process it. Okay, so I've talked about compound variables and I've talked about stacks, and both of them process a large or unknown number of things. And so why would I use the data stack? Well, in Rexx, if I want to pass data to another program, I have two options. One is I can pass it as parameters, right? So I just pass some parameters to the other program, and the other program does a parse arg, and it parses the arguments that I passed. But I cannot pass a compound variable between programs. I can only pass single variables between programs. So want to pass a large number or an unknown number of arguments between programs, between Rexx execs, then I'd use the stack. So what I typically would see is my program that wants to pass the data pushes several things on the stack. And then the other program that needs to receive the data issues the queued function to find out how many things there are, and then starts pulling them off of the stack. So that's one reason why people use the stack instead of compound variables. The other reason people use the stack is when your exec ends, when your Rexx exec ends, if there's anything left on the stack, it gets executed as commands in the environment you return to. So if you're in CMS when you're calling a Rexx exec and your Rexx exec ends and you've left things on the stack, those things are going to get treated as CMS commands and get executed. Now, that may not be what you want, which is why you need to make sure you always leave a clean stack. But what other people have done is they've used that as a way to sort of script responses to an old program someone wrote that needed a human being to respond at the keyboard. And we want to avoid that and automate the process. So we stack the answers, if you will, to the questions on the stack, end the program, and then the other program will run and read things off. So it's a trick people use when they have older programs that require user intervention and they want to avoid that. But the more common case is I need to pass data between two programs. So let's just do a quick example of stack processing. So this is a typical situation you would see. I'm a receiving program, somebody else called me, and I need a bunch of data that they had. So instead of writing that data to disk and doing I/O and making the second program read that data, I can just pass it on the stack in memory. So typically my receiving program would just put that data into a STEM variable where I can process it more easily for the rest of my program. So I say element.0 equals queued. Remember, queued is a function. It must return a value. So it's typically on the right-hand side of an equal sign. I put the number of things on the stack into the .0 of the STEM variable element. And then I just go through the do loop processing from 1 to element.0 everything that's on the stack. So until the number of things on the stack is empty, I'm pulling one entry at a time and putting it into the variable called element as a stack. So that's a very typical use case that you would see of how to receive the data. The inverse is true for sending the data. I basically just go through maybe my STEM variable and I push it on the stack, right? So that my receiving program can receive it. Okay, now remember when I'm parsing and I'm doing a parse pull, I have full parsing capability here. So I don't have to just pull off one value, right? It can be a long string of values that contain many things that I want to actually parse and put into different variables or different STEM variables. So maybe I'm passing, name value pairs or something like that, right? On a single stack entry is the name and the value. And I want to break those into two different STEM arrays. I can certainly do that by just putting more variables out here on the parse pull statement. Okay, so no, you can't really have multiple stacks, but you can sort of start inserting things in a new place. So there's something in Rexx called buffers, the make buff command and the drop buff command. So what happens is if you issue the make buff command, Rexx will create a buffer on top of your existing stack so you could actually put things on the bottom. So here's my old stack here with elements 1 and A, and maybe I want to have something new. I want to sort of set that aside and process a new set of things that I want to be in, first out order instead of last in, first out order, right? So I want to process these new things first in, first out without touching these old elements in the stack. So what I can do is issue the make buff command. It puts sort of a marker here. And now when I issue the queue instruction, instead of inserting it down here below old A, it actually inserts it here. So I could do multiple queue instructions. So I would have done a queue for X. I would have done a queue for Y. I could do a queue for Z, and they'll be in that order on the stack. Okay, so queue would insert on the bottom of the stack. Typically, you don't need to do this if you're just going to push things on the top of the stack anyway, right? Because you already have an existing stack and you can just push things on the top and go down and process them from the top of the stack. You would typically only use makebuff if you have a stack and you want to start inserting things in a different order. And you want to use the queue instruction instead of the push instruction. So the exec uses makebuff to create the buffers. Makebuff will actually give you a value in the RC variable, the return code variable, identifying the number of the newly created buffer. So if it's the first buffer you created, the return code will be 1. If it's the second buffer you've created, it's the return code will be 2. The drop buff command is actually used to remove a buffer from the stack. So it's like if you've put 5 things on the stack, you do a make buff, and then you want to put 5 more things on the stack, and halfway through those 5 things, mind, I don't need the rest of the data. I can use a drop buff and it gets right back to the original stack. Okay, so that's what the drop buff command is going to do. But the other thing you can do is just keep pulling from the stack. So if you just keep pulling from the stack back here, if you did a pull, you would get new X. You do another pull, you'll get new Y. You do another pull, you're just going to go right into the other stack and do an old one, pull old one. So there's no sort of protection of the original stack if you're not keeping track within the code of how many things you're adding to the buffer. Okay, it's still considered a single stack by Rexx. You've changed the insertion point by using the make buff command. Now, in ZOS, there is a function called qbuff, or that's actually a command to find out how many buffers have been created. We do not have that function in ZVM. So you have to keep track when you use make buff how many times you've done that, how many buffers you have on top of the stack. The qElement command, also a ZOS only thing, is used to find out how many elements are in the most recently created buffer. So in ZOS, if I did a qElement here, I would get 2. If I did a queued, then I would get 4. Okay? In ZVM, our only option is to issue the queued function, and that's going to give me 4. I have no way in ZVM of knowing how many things are in the most recent buffer. I have to keep track of that myself in the code. As I'm putting things on the stack, I need to be incrementing a counter somewhere. Okay? The other thing to be aware of is the drop buff 0 will result in an empty stack. So buffer 0 is considered the main stack. This is considered buffer 1. This is considered buffer 0. So if you do a drop buff for 0, it takes everything out. Okay, so you're basically emptying the stack, which may be what you want, may not be what you want. If there's nothing on the stack, it doesn't hurt. So if you're concerned about, you have several things on the stack, you don't want to go through and pull them all off before you exit the program because you don't need them, you can just do a drop buff 0 and it will get rid of everything in the stack before your program exits. Because remember, I said when your program exits, if you leave anything in the stack, it gets executed as commands in the environment that you return to. Okay, so when the buffer is empty, as I said, the next pull automatically pulls the next item in the stack. So there is no error or indication, there's no information to indicate that you've moved from your buffer into the main stack or from one buffer to the next buffer down in the stack, okay? You have to sort of remember and know what you're doing there. And again, buffers only change the insertion point for a FIFO stack. That's really all you're doing by using buffers. You're not protecting the main data, you're just changing where you're inserting data. So you really have to make sure you're keeping track of it yourself. If you want to remove a buffer that still contains elements and you want to remove just a buffer, you issue drop buff, remove the current buffer. But again, if you want to drop everything, you can just do a drop buff 0. Okay. So another function that's ZOS only, so I'm sorry that we don't have this in ZVM, is the ability to create a separate stack. So it's not a buffer on top of the existing stack, it's a new stack, okay? So there is a new stack command that allows you to do that. When you add elements, you can only add elements to the new stack. Once you've created this new stack, you cannot go back and add elements in the original stack. Okay. You also cannot pull elements from the original stack. You can only pull elements from the new stack. So the difference here is between buffers and this, right? This might sound like a buffer, right? All I'm doing is changing my insertion point. But the difference here is when this stack is empty, when new stack is empty, if you do not delete it deliberately, specifically in your program, then it's going to action the terminal instead of the original data stack. So it does not automatically move from new Y to old 1, right? If I pulled off new X, I pulled off new Y, and then I did another pull, if this was a buffer, it would pull off old 1. But because this is a stack, it doesn't pull anything off the stack. It goes to the terminal and prompts the user. So that's the difference. But again, this is a ZOS only thing. If you do want to delete the stack and move back to the original stack, there's a del stack or delete stack command in Rexx to do that. So that's all that does, is kind of move you back to the previous stack, because you might have multiple stacks, right? I'm showing 2 here, the original one and the new one, but I could create 2 or 3 other stacks as well. And every time I do a delete stack, it goes back to the previous one. Okay. And then because I have this function, qstack in ZOS will tell me the number of stacks that I have, including the original one, and puts that value in the variable return code. And also in ZOS, the queued function, because this is now a new stack, the queued function in ZOS will return the number of elements in the current stack, not the total elements across all stacks. And when you're using buffers, queued will return everything in the buffers and the stack. When you're doing new stacks, it will only return data, the number of things in the new stack. Okay, so why would I use data stacks versus buffers? So the data stack, the advantage here is, it protects the original stack. You have to specifically and deliberately go back to the original stack. It just will not default back to it. The disadvantage, of course, for those of us loving ZVM is it's only available in ZOS. If in ZVM you have data on the stack, but you want to prompt the user for input and not pull from the stack, you would use a parse external instead of a parse pull. So that's a case where you want to get something from the user, you use parse external. When you want to pull something from the stack, you use parse pull. So buffers, of course, are supported on both ZVM and ZOS. I'm creating a stack on top of the existing stack because I want to insert items on a new bottom, if you will. I want to define a new bottom point. In ZOS, I have the nice quElement function to see how many elements are in the buffer. But the disadvantage here is it doesn't do any protection of the previous stack. As soon as I go through my buffer, it will go down to the next buffer, go to the next buffer, and go to the main stack without any indication to you with a return code or anything that it's doing that. So why would I use compound variables versus a data stack, right? I've talked about both, and I've alluded to this already. So compound variables, really the advantages here is they're basically just other Rexx variables. So it's easy to process things in one step to assign a value. The disadvantage is I cannot use them to pass data between programs. So if my Rexx exec calls somebody else's Rexx exec or another Rexx exec I cannot pass data in a stem variable to use the stack. So what I typically say is use compound variables whenever you can because they are simpler to use, but use the stack obviously when you have to. So again, the major advantage of the stack is I can pass data to other routines. And if I am trying to automate some older routine that prompted users for input, and I'm trying to avoid the prompts and just automate the process, I can sort of use the stack as my way of stacking the responses and getting the routine to pull from those. The disadvantage of the stack is I now have to manage the stack, right? I have to take things off, I have to put things on, I have to make sure they're in the right order, and it typically requires 2 steps. I have to put things on the stack, call the other program has to take things off the stack and put them into a compound variable. And of course, the other disadvantage here is for people who are writing code in ZOS natively, you might be using functions that are not going to be available if you move that code over to ZVM. Okay? I'm going to just spend a couple of minutes on I/O, and then we'll spend a little bit of time on troubleshooting as well. So in ZOS, I'm not going to spend a lot of time on this. Exec I/O is typically the way people are going to read things from files in Rexx or do I/O, read and write files. The data can be written or read from or written to compound variables or the data stack. So again, easy ways you can take a whole stem variable and write it out to a file in one instruction. In ZVM, there is an exec I/O function. I strongly suggest that you ignore it and you go look at pipelines instead. Pipelines is going to give you a lot more power and a lot more function, a lot easier to do I/O processing and many other things, of course, in CMS pipelines. But even I/O processing is just much simpler and easier with CMS pipelines. So here's an example of 2 commands that do exactly the same thing. One is written in the exec I/O format and one is written in pipelines. They're both taking the stem rec and they're reading the file employee info and assigning it into the stem variable called rec. And again, remember, in both cases, the .0 value of rec will be the number of elements that it read or the number of records in the file. I think there's a whole different pipelines class, but I'm just encouraging you, if you're looking for I/O, do not look at exec I/O, look at pipelines. The other thing to keep in mind as you're doing any kind of I/O or troubleshooting is there are special variables in Rexx. I've talked about these in various places already, but just consolidating here that these variables names, RC and result, are something you never want to use in your program for your own purposes because Rexx will overwrite them depending on what other instructions you're issuing. So these are sort of reserved by Rexx to use. It's not going to get any kind of an error if you do use them, other than the value will not be what you think it is because you probably issued some other command and changed the value. Okay, so let's spend a few minutes on troubleshooting here. You should never learn a new language without knowing how to troubleshoot the language. So first, there's a couple of instructions in Rexx that we can use to sort of trap exception conditions. So what this is a way for you to say, if I have some kind of a major issue in my Rexx program, and we'll talk about some of the information below, what the conditions are. But if I have a major error, I can sort of just exit the program or exit to another routine and either return or not return to my original calling program. So the signal on or the call on instruction would typically be something you put at the start of a program, and you would say signal on and then one of these error condition types, right? So if I have a syntax error, right, I would say signal on and then syntax, and then where do I want to go in the program if I have a syntax error? So instead of just sort of ending the program with this syntax error, I could actually go to a subroutine in the program and do some kind of processing before the program exits. The call on does exactly the same thing, except it actually returns to where the Rexx program had the problem, and it returns to the original processing. So signal on and call on are things that you specify typically once at the beginning of the program for any or more of these condition types, and then your program will react accordingly. Now, I will tell you that, of course, if you're compiling your Rexx code, you should never have a syntax error. But I will tell you that lots of people use the signal on no value as a good way to make sure in their program that they've initialized any variables that they want to use. I think I talk about this. Yes, I talk about this on the next slide. So a good practice that you'll see in some Rexx programs is signal on no value, name, and then the name of the error routine. This will get called whenever in your program you reference a variable and you have not initialized it. So it's sort of that eye catcher. Remember I told you about Rexx variables have their initial value of their name in uppercase. So if you're debugging code and suddenly you see one of your variable names in all uppercase, it usually indicates that you've not initialized it. This is another way to let Rexx tell you when that happens. So it will tell you sometime in the program, you're referencing a variable, you've never assigned it a value. I'm going to exit the main program, go to some subroutine and do some processing, and then exit the program. If I had call on no value name, then I would have the same thing would happen. I'd reference a variable that was not initialized. I would go to my error routine, but if I used call on, then it would come back to my main line of processing. So maybe I want to have call on and I'm going to just initialize it to a null or something before my main program continues. So lots of things I might want to check here. And once I'm in that subroutine, I have access to data about what's going on in the program. Okay, so I have access to the condition function. What was the function that led to this problem? Was it a syntax error? Was it a no value error? I have error text, so I have the actual error message available to me in the error text return code, and I have the actual line of code that caused the error in a function called source line. And so I have information that I could then use in my subroutine to maybe do my own error processing and recovery, if you will, right? If I know what I want to do in these situations. Now, you shouldn't normally use this as a way of, having lazy code, doing lazy programming, right? These should certainly be exceptions that just might help you do things easier when you're debugging or running a code in a test environment. Okay, so trace is your friend. Trace is a wonderful instruction in Rexx. And the beauty of the trace command is it has multiple options, so I can specify the level of trace that I want. And the best thing about trace is I can insert it anywhere in my program, and I can change the level of tracing anywhere in my program. So I might start my program with trace off, and then if I know I have a troublesome piece of code, I can turn trace on right before that section of code. When that section of code is at the end of that section of code, I can turn trace off again. Or maybe I want to change the level of tracing throughout the program. I do more deep level tracing in this one section of code and do a higher level tracing in the other section of code. So it's very, very flexible. It's not like most other languages where once you turn trace on, the whole program is being traced, and you have to look through 100 lines of code that you don't care about that you know are working before you get to the ones you do care about. In Rexx, you just put the trace instruction exactly where you want it to start tracing. So let's look at some examples. There's lots of options you see here. I'm not going to go through all of them. I'm just going to go through kind of the most common ones. So in this code example, I've assigned some values to the variables A, B, C, and D, and then I've inserted the trace instruction. So I have not done any tracing before this, and now I have trace R for trace results. And in my code, I'm saying if A is less than B or C is less than 2 times D, then I want to say at least one expression was true. Otherwise, say neither expression was true. So what happens with this code when I execute it with the trace R where it is? This is the result I'm going to get. I'm going to get the result of that line of code of execution. And so the result of this if statement is 1, meaning that it's true. So a 0 means false, a 1 means true. And since C is less than 2 times D, C is 3, 2 times D is 8. So one of these statements is true. So the whole statement is true. So that's the result that I'm going to get when I run this program with trace R. Now, maybe that's not good enough for me. Maybe I need a deeper level of tracing. Maybe this is a very complex statement here, and I want it to sort of break it down into the details. Use trace I instead. So I have the exact same code, but I'm using trace I instead of trace R. Now you'll see my output is a lot more detail. So now this one line of instruction, instead of just producing one line of output saying that it's true with the number 1, I'm actually going to evaluate each thing in the line and output that information. So let's walk through this. The first thing it does is tell me that there's a variable and it has a value of 1. That's the A. The next thing it does is it says that there's a variable and it has a value of 2. That's the B. So then I say the output of the operation, A is greater than B, is 0 because 1 is not greater than 2. So the O here says I have an operation and the output of that operation is 0, which is false. Now I'm going to move on and I have another variable whose value is 3, and that's the letter C up here. I have a literal, which is the number 2. So this is a literal. That's the 2 right here. I have another variable whose value is 4. That's the D. And now I'm doing the output of an operation which has a value of 8. And that's the 2 times D because I do that operation first. And then I have an output of another operation, and that value is 1 for true. So the question is C less than 2 times D? And the answer is yes, it's true because 3 is less than 8. So the output of that operation is true. So now the output of the whole statement is true because it was an OR statement. So one side was false, one side was true. So the output of the whole operation is true, signified by the value 1. So I get a lot when I do trace I. So you want to be careful with trace I. But again, the beauty of trace is I could do a trace I for these instructions, and then I could change it to trace R and do a much higher level of tracing without all the deep dive for maybe another section of my code. So very handy. There are also other options in trace. Here we go. So we have an interactive trace. So if I put the question mark in, instead of doing a trace R, I could do a trace question mark R. And what that means is every instruction that Rexx executes, it will stop and wait for you on the console to hit enter, meaning continue, or you could actually issue instructions on the command line to turn the trace off, change variable values, all those many, many powerful things you can do while the code is running. So you can literally change the execution path of the code while the code is running. So the question mark is very handy when there's a piece of code you really want to dive into and issue commands on, but it's obviously going to pause at every instruction and wait for you to hit enter. Okay, so this next topic is a very, like most things that have the word style in it, it's a very personal choice, right? Everyone has their own style. What I'm going to say here is the most important thing is to be consistent in your style. Whatever you choose, be consistent so that the next person reading your code understands your style and knows how to read the code easier. I will say, though, that a couple of things, indentation will help improve readability. So when you're doing if, then, else statements or do loops, as you saw in my examples, the lines between the do and the end are indented. So you can very quickly glance down and know where the end of the do loop is. If you have multiple statements in a then statement, right, you need a section of code and then an end, you want to line up the then with the end so we know where that section of code ends before it moves on to else. So very, very not important from a Rexx standpoint. Rexx doesn't care, but from a human readable standpoint, it's pretty important. Of course, comments, as we all say, which we, is hard for all of us to do when we're writing our own little piece of code. The most important thing is to provide them. And Rexx gives you a couple of ways to do that. You can either do block comments, so a whole line of instructions is a comment, or you can actually have code, and then to the right of the code, you can have a comment as well. So you can put comments right on the same line as the code, or you can put a block of comments, if you will, maybe before a section of code. So totally up to you how you want to do that. But here's my suggestions. Again, these are my suggestions of kind of some ways if you're just starting with Rexx and you're looking for some recommendations on, what's kind of a good style or a good programming technique to use to indicate what your consistency is. The first thing I would say is use capitalization. And we'll talk about where to use it. I try to use capitalization on instruction that I'm calling. So anything that's Rexx specific, I'm going to use capitalization. I'm going to capitalize the first letter and use lowercase for the rest of it. I'm also going to suggest for your variables, you always use all lowercase. So you do not use a mix of uppercase and lowercase for your variable names. Use all lowercase, so then it's easy for someone to distinguish between either a Rexx instruction or maybe even one of your function calls that is a capital letter to start versus your variable names that are all lowercase. And if you're calling to an external routine, assuming that that external function accepts all uppercase, you're going to want to put your command in all uppercase. It just also makes it sort of stand out as this is something I'm calling outside of Rexx. I'm issuing a CP command. I'm issuing a CMS command. I'm calling another Rexx exec, those kinds of things. So it stands out by having the whole thing in uppercase. Every Rexx program needs to start with a comment. And in Rexx, a comment is a / followed by an */. So that's the way to indicate to ZVM or to ZOS that this is a Rexx program. Otherwise, ZVM will default and assume that it's in another language. I believe it's going to assume it's in exec2 or exec, very old ZVM languages. So you must start every program with a comment, even if it's a blank comment with a / and then an */. Now, in terms of your variable names, I know it gets really easy when you start typing to just start using single letters, right? A, B, C, D, whatever. But that doesn't really help the next person who's reading your program, right? And for most of us, there is going to be somebody else who's going to inherit our code or want to look at our code and steal something from our code. And so these one character names are really not helpful to them. So it's good to use meaningful names. There's no 8-character limit in Rexx, so we don't have to worry about that. We can actually use real words. And the exception I have to the 1-character name is when you're using them as indexes to a compound variable or a stem variable. So you'll notice in the presentation, my do loops, I said do j equals 1 to whatever, right? Do I equals 1 to whatever. I think that's perfectly fine to have a single character there just to indicate that it's an index. Also, something that people don't think about is I like to avoid ending variable names with the letter O or the lowercase l, because in some fonts, that's difficult to distinguish between 0 and 1. So I try not to use those at the end of names where people might think that that's a 1 or a 0. Obviously, if you're using an L in the middle of a word, if you have a variable named hello, using L's is perfectly fine. People read that and they can see the word hello. But if you have it at the end of a word, they might think that you're going to use multiple variables, 1, 2, 3, 4, 5, and they might think that that L is a 1. And then same thing with your zeros. Okay, so the other thing to think about in Rexx is when you're doing comparisons, whether blanks are included in things is something that you can actually distinguish between. So we usually think of the equal sign, meaning things are exactly equal. But in Rexx, what that really means is that they're equal, except one of them might have more blanks at the end than the other. So if you really want to look for exactly equal, no matter whether you want to count the blanks at the end, then you need to use the double equal sign. Otherwise, if the action is save with a blank, the equal sign will show that it's equal to save without the blank. The double equal sign will show it's not equal to save without the blank. The other thing to think about, again, Rexx runs on other platforms as well. I know many of us are ZVM and ZOS, but the Rexx language actually runs on other platforms and can be quite compatible. So the only thing that is not compatible is some of these special characters that we in the Z world use for not characters. So the caret, if you will, the not equal sign, the slash. I avoid using those kind of non-standard characters because they don't really transfer to the ASCII platform very well. So typically, if you're trying to say not equal to something, the best thing to do is use \equal to indicate not equal. The other thing I'll suggest is you'll see some people have semicolons at the end of every line in their exec. Semicolons can be used within Rexx to put multiple statements on one line. So it's an indicator of an end of statement. A semicolon is an end of statement character. So if you wanted to put multiple statements on the same line, you would use a semicolon to separate them. But the problem is if you put them on every line without any kind of need, if you're not putting two instructions on the same line, you're just using one line per instruction, like normal coding or typical coding, and you put the semicolons at the end just thinking that you're being very specific, it actually does two things. It detracts from the readability because now you've got the semicolon at the end of every line, but it also gives you additional processing for Rexx to do, right? Rexx is now processing that extra character as an end of line and looking for more data. So it actually adds to processing time in Rexx. The other thing to think about is things that can get you in trouble. If you start doing complex statements, Rexx will always evaluate all of the Boolean expressions, even if the first one fails, or even if the first one succeeds. So for example, if you had an if statement, if you said if 1 equals 2 and 3 equals 4 and 5 equals 5, then say this is impossible, right? Then that's okay. But if one of those you were trying to do some kind of a function and divide by 0, it can get you into trouble. So maybe I want to say if A is not equal to 0 and B over A is greater than 1, maybe I think I've avoided the divide by 0 because the second one would not be executed unless the first one was true. That is not the case. I'm going to always evaluate both of those. So if A is equal to 0, the first half of it would be true, but the second half would give you an error because you're trying to divide by 0. So instead, you have to nest your if statements. So you have to say if A is not equal to 0, then if B divided by A is greater than 1. So you have to nest your if statement so that that second one is never executed if the first one is not true. Putting them on the same line with an and statement does not solve that problem. Okay, the last thing is, I said every variable, its initial value is its name in uppercase. So some people might have a Rexx exec and they just know that they're not using some specific variables and they happen to be commands, right, in ZOS or ZVM. So if they had a program that issued this statement, control errors cancel, Rexx is going to look for the value of the variable control, look for the value of the variable errors, and look for the value of the variable cancel. If none of those had been initialized, it will actually execute a command, control errors cancel. And maybe that's what the user wanted, knowing that that's what would happen. But if they had assigned a value to any of those variables, then the command would not work. So we have to be careful with this. Whenever we have literals of what we're actually trying to process, we want to put them in quotation marks to be very clear to both Rexx and to the next person reading this program that that is a literal. It is not subject to variable processing. Okay. Also, Rexx is going to take time looking up those variables. And if you did not intend for it to do that, if you knew all along that you did not initialize those, wanted their values to be their names in uppercase, then you've just wasted extra CPU processing in your program. So if you have literals for commands, you always want to put them in quotation marks. Do not rely on this fact that this Rexx will translate them to uppercase if they're not initialized. Okay, I'm going to jump ahead to a couple of other things to make sure you're aware of other Rexx-related programs that are out there. So we already talked about pipelines, so certainly that's something you should be looking at and learning along with Rexx as well, because pipelines is going to give you a lot of function that you can do in maybe one line of processing versus maybe a loop in Rexx, those kinds of things. So you should always be looking at pipelines to improve things as well, and certainly for your I/O processing. There is something called Open Object Rexx. So this is the object-oriented Rexx language. It is out there. It's 99% compatible with IBM Z Rexx programs, but it does have object-oriented function. That's out there as open source. It's managed by the Rexx Language Association. So if you're trying to do Rexx on other platforms and you like object-oriented languages, you might look at OORexx. And then we have NetRexx. So NetRexx is another language, again, open source, managed by the Rexx Language Association. What it does is take your object-oriented Rexx for Java. So you write your code in Rexx or Rexx-like, and then the compiler will convert it to Java source statements and bytecode. So if you don't want to write in Java, you want to write more in Rexx because you're just trying to do something simple, but it needs to run in Java, then you can write it in Rexx, but it will execute in a Java virtual machine. And with that, I will wrap up. There's more information on the Rexx website. Thanks.
Thanks for watching. If you enjoyed this video, don't forget to like and subscribe to see more videos like this one. Have a suggestion for another video topic? Feel free to leave a comment below.